Okay, here we are looking at electric fields. Essentially, this is the first of three topics with electricity. This one talks about how potential difference is created, and then we're defining things like current and charge. So first up, we'll look at charge. Now, we know it's around, it has an effect. Originally, they first looked at charge in terms of static charge, okay, so build up of certain charges on different objects. Now, all we really know is that charge can create areas, or like an electric field, which is an area where other charges will feel a force or that type of thing. So, to actually describe what charge is very difficult, and in fact, there is no real description. When we do define it a bit later, we'll define it by the formula. Uh, it is based on current. Okay, so current is used to define it, not the other way around. Now, generally for charge, we don't really look at a balanced charge. It's not very important to us. We look for unbalanced charges. So an unbalanced charge leads to lightning in the picture. It also leads to a voltage difference or potential difference, which you can then use to light bulbs and so on. Now the coulomb is the unit of charge. Okay, the symbol for the coulomb is C. Now, what the coulomb is equal to? Okay, so 1 coulomb is equal to what happens when you have 1 ampere of current flowing for 1 second. Okay, so that's how much a coulomb is. So it's a certain size of charge, and you can see that because it's just 1 ampere multiplied by 1 second, these are just units that have been created, and it's created another unit from it. Okay, so ampere is a base unit, seconds a base unit, and those have been this has created this coulomb unit. Now, really, an ampere I don't really get into, but that is actually the size of it is defined using force, which you can look at in A2 physics. Now, the formula for charge is Q equals IT. Okay, and it's also could be used as the definition. Okay, if you use words. Okay, so Q equals IT is the formula for it. Now, electric current. Electric current is the rate of flow of electric charge, and it is a base quantity. Okay, or you could say it's the amount of charge that flows past a specific point per unit of time. Okay, so something like that. Now, for example, if a circuit has 4 amps flowing through it, how much charge passes a point in 12 minutes? And for B, how many electrons are required to make this charge? So, answer for A, we're trying to find how much charge, so Q passes a point in 12 minutes with 4 amps. So, Q equals IT. So, current is 4 amps multiplied by 12, and we want it in seconds, so we're going to multiply it by 60. Okay, you can go from there. And for the second one, how many electrons are required to make this charge? Well, the charge on an electron, okay, is Q. It's usually called E. Okay, is 1.6 times 10 to the minus 19 coulombs. So the charge on an electron, in fact, is very tiny. It will take a lot of them to get the charge up here. Okay, so all you want to do is find out from this charge, okay, we're going to divide that by 1.6 times 10 to the minus 19, because that will tell you how many of them go into the charge we calculated in A. Now, when you have charges, these pictures here show an unbalanced charge. So this one here has more electrons than protons. This one here has too few electrons. These two both have too few electrons. So in other words, there's more protons than electrons in these molecules or objects. This one here, these two will be attracted to each other. So those arrows represent some sort of force. Okay, so the first one is just the general rule of charges. Like charges are attractive. Okay, so like charges attract. And the last one here, unlike charges repel. Now, a test for the law of charges, okay, we'll describe this in class, but generally, if you hang a piece of plastic on a string so it's free to rotate, you bring another charge close into it, it will see repulsion. Bring another charge in, you might get attraction, okay, and so you can work it out as long as you sort of know what charge you're bringing close. Now, using an electroscope. Now, essentially, an electroscope is a piece of metal bar. Okay, so that there is a nice metal bar. Okay, a metal plate at the top, and on the side of it there will be a gold leaf. So we'll make it red. So there's a gold leaf. Now, if you bring a charged object close, okay, so here we have a negatively charged object. You bring it close, and what it's going to do, we know that negative charges repel from another negative charge. So that means all the negative charges get forced down this way. Okay, so all the negative charges go down there, and they also go down the gold leaf. Now, because negative charges repel, like I just said before, well, these two things here are going to repel each other, and the gold leaf then is also is really thin, so it can bend easily. So the gold leaf is going to move up and then become move to a different position out there, and that will show that we have a charge to the electroscope. And it can happen the opposite way. If you bring in a positive charge, you can draw electrons up to the top, and it will then be charged and it can move out again. So remember, only electrons can move, and there's also some other effects that can happen too. This is the picture of it, nice picture, and shows you what could happen. Now, a couple of applications of this stuff. One is spray painting. So let's say you charged up your spray paint, and as it went past, okay, you made it, let's say you made it some sort of positive charge or something like that. And then if you charged up your wall, okay, or whatever you're painting, like a car or someone, and you made a negative charge, then the paint, as it sprays out, real fine jet, will attract to all points on the object, okay, and usually quite evenly, because there's going to be a nice spread, because the particles don't like each other in the paint, but they do like the frame that they're trying to land on. And that's actually how they do cars and so on. They would charge up the car, the metal body, before they spray it. Dust extraction, very similar. So let's say you're working in a laboratory, don't want dust. What they would do, they would fire air through a grill. Okay, so this blue drawing here, that will show your ducting. Okay, nice diagram there. So there we go. There's your ducting. Now let's just take a little bit off there. Take this bit there. Good. So that's your ducting, and we've got a grill inside the ducting. Now, generally, dust is charged, okay, especially if it's flying through a metal tube. The metal tube itself will actually charge it up. So what you can do, or even by induction, it will actually charge itself. So what you'll do is you'll put a large voltage on this plate here, sorry, on the grill, and what that will do, as a dust particle comes flying in, it's going to get charged. So if this thing here was a large positive charge, then this thing is going to have a negative charge at the front, positive charge at the back. Negative is closer to the positive, so it's going to attract stronger than it's going to repel, and then you actually then get dust stuck all around the grill. Okay, so little dust particles then attached to the grill, and none gets through. So that is dust extraction.